The next important topic, that is the drying kinetics, or you can shown as the drying means in case of drying process how the moisture is removed from any particular food material. So how can we represent this data, or how can we know this, what are the exact time required during this entire processing. So when we are representing drying, so we this present in terms of moisture content, means that can be removable. We also called as the free moisture content, and here we represent in terms of time. So drying rate means moisture content versus time plot, that will give us the drying rate, means moisture removal rate per time. So you see that here graph is like that, here one break, one, and this at first denoted in, let us say it is P, Q, R, S, T. Same graph we can representing like this only. Here what we can do, here we represent in terms of drying rate, means how much amount of water that are removed per area of food product in terms of time, and whatever the moisture present in that food product. Here this you can see that the two graphs are different, and but both are representing same data. Here this graph is like that, this and this. From here the graph starts in this direction. In this graphical presentation the graphs are presenting in this direction, in backward direction. So what is that? Means here representing is free moisture content versus time plot. Here plot is the drying rate versus free moisture content. This is known as the settle down period, or majority of time it is neglected. And this QR is shown as the, this is like this way, QR zone, but straight line with it is known as the constant rate period. And in RS to ST, this is like you can like falling, this is constantly going, but certainly this is falling. So here it is denoted in falling rate period. And you can also see that here is the break, segregated. This is the first falling rate and this is the second falling rate period. First falling rate and second falling rate period, means. So let's come from this small zone, this is zone PQ. As I told, this is the settle down period, means when any product directly comes to contact in terms of high temperature environment, that this zone is representing this data only, means directly comes to equilibrium with the drying air. When the directly comes and equilibrium with the drying air condition, this zone is the known as the settle down period. It is very smaller duration, but sometime it is also neglected. Some majority of time they are representing majority of books or research article, they are started with the constant rate drying period and then going for the falling rate drying period. But this zone is very small, it is very difficult to calculate, so we neglected it. If what is the settle down period, means the at the beginning of this drying process, when they are kept in a feed any material to drying chamber, so that will that is comes from the environmental temperature for say 25 degrees Celsius if any material is kept on that, and it is suddenly 50-degree drying temperature. So it will take some time to adjust this environment and with the surroundings and to reach this equilibrium condition with the drying air as the settle down period. Here also write time T0. P is represented as the initial free moisture content. Initial moisture content usually very short, as I told, and may be ignored. So the next topic is the constant rate periods. Constant rate, how constant means constantly removed the moisture content. Constant rate means rate is constant during this entire process. Also we remember in like that way, in constant rate drying period the moisture removal rate is constant with respect to time or with irrespective of any types of material. It occurs at the wet bulb of the temperature of the air. Here what happened? Here continuous films of water, whatever the moisture present in this product material surroundings, that will easily comes to out, and here the moisture, here this rate is drying rate is constantly maintained. So means also represent the continuous removal of moisture content is directly exist on surface, and evaporation occurs, evaporation from this film of this water means whatever the moisture is removed from the material, that is continuous process from the outside periphery of the surface. And during this process what can we known or what is the process for depends, it is depends on heat and mass transfer coefficient, and surface area is very important for any types of process, any types of for calculating drying constant rate or falling rate fluid, because and temperature. If we increase the temperature, initially the moisture removal rate will be high. And in humidity, also plays the same role here, and also the difference between temperature and humidity. If the difference is higher, then the process will takes place in rapidly. Air stream and wet surface of the food material. For example, if you are feeding any material having temperature of 30 degrees Celsius to 50 degrees Celsius, means the drying process will takes place very quickly. If you are feeding like 10 degree temperature in 50 degrees Celsius temperature, so this drying process, initial starting drying process will be takes much more time as compared to earlier one. So then the next point is the movement of this water, means whatever the moisture present in this food product inside to outside, means interior to surface is greater than the rate of evaporation, means assume this is food material that we are going to dry, means whatever the moisture present that will comes outside or surface of the food, and from the surface this moisture is evaporated to the surroundings. In this condition what happened? Constant rate drying period, the moisture removal rate from inside to outside of this surface of this food product is higher as compared to the drying rate. So when this value will be, until and unless this value will be lesser, till now this constant rate drying period is maintained, and also the rate of drying is controlled by the rate of diffusion, means the moisture removal rate from inside to outside, that is also known as the diffusion, from internal to outer. So diffusion, so this diffusion rate is also controlled by the drying time, drying rate. If this diffusion rate will be slow, then the entire drying time will take much more time. It is diffusion rate will be faster, then entire drying time will be take less time. Then the next topic is the critical moisture content. Critical moisture content from that point, means this is known as the constant rate drying period. After this point the moisture is losing like this way, means non-linear curve they maintain. Moisture is removal rate is maintained. So this is known as the critical point. This is very important terminology. Means here point R is represent critical moisture content. End point of the constant rate period means this is the ending point of this period, this critical constant rate drying period, and the starting point of the falling rate period. After this point the falling rate start. So what are the changes takes place during this process? First one is the surface temperature. What about the surface? For example, it is denoted in x1. For example, in constant rate drying period. After this critical moisture content reaching, then the temperature may be rise to x2. That is, x2 is higher as compared to x1. The moisture content is decreased, means the free moisture that are easily removed, that entirely removed by this constant rate drying period. And rate of diffusion means whatever the moisture is comes to internal to outer surface, so the rate will reduced. And then the rate of drying means what moisture removal rate is very slow. So topic wise, surface temperature will rise after the completing of constant rate drying period, then moisture content decrease, then rate of diffusion will be decreased, means the drying rate also very slow. And the next one is the falling rate period. It can be classified into two ways. First one is the first falling rate period and secondary is the second falling rate period. Means this RS is known as the first falling rate period and then ST is known as the second falling rate period. So what happened in first falling rate period means no longer to internal to outer surface of this food material to the surface. So this is unsaturated surface drying, and so that's why the moisture removal rate is also lesser. So in case of first falling rate period, the moisture content in a food material does not comes from internal to outer surface in a systematic way, means they are not sufficiently comes to the outer surface, fine as the unsaturated condition, means no saturation exists, only the whatever the moisture that will comes from internal to quickly removed, and then the same drying temperature is not only increase the vapor pressure of this material but also increase the surface temperature of the food material. And second falling rate, what happened? So and this same condition is repeated, so that what happened, the entire surface of this food material was completely dry, but the outer environmental temperature is high as compared to food material, so that will completely dry the outer surface of this material. So and the next point is the drying rate is mainly limited, restricted, or you can solve as the restricted by the diffusion rate. Whatever the if the diffusion rate is slow, then drying rate also slow, and in this second falling rate the diffusion rate is very slow. So that's why on another way you can say that constant rate drying time is smaller and falling rate drying time is much bigger. Evaporation rate from the outer surface is very small. So what we can conclude this entire drying rate curve. So falling rate period is higher as compared to constant rate. You can see this falling rate contain this entire this zone, and this constant rate contain this zone only. Evaporation of water is very small, means this entire surface, this entire zone, you can see that this much amount of moisture is removed, and in constant rate drying period this much amount of moisture is removed. And one thing you can say that, one thing you can remember also, that majority of entire drying process mainly takes place only in falling rate period. Whatever the moisture that it can be removed by constant rate drying period, that is very lesser quantity, and majority of drying process in this only takes place in falling rate drying period. So that's why falling rate drying period is the key parameter of any drying process of that particular product. How to calculate the amount of moisture that we can remove, this whatever you can say, this constant rate, falling rate period. So what are the equation for that? So this RC is mainly defined as the rate, how much amount of moisture is removed, that we can directly present in dm by dt. M means amount of water that are removed by this process, T means with respect to time. Here xi is the represent is the initial moisture content of the food material, and xc is the critical moisture content of this food material. So subtract that will give us the moisture removed. If we divide it by in terms of time or entire duration, that will give us the rate, means whatever the moisture removed by this time, that will gives us the rate. You can express in terms of minute or hour or sometimes second also. In terms of another terminology, means this vapor pressure terminology, if you want to calculate mass transfer coefficient using, so what are the terminology required if you want to known as the drying rate? So kg into A into Pw minus Pa. Where is Pw? Pw, when they are representing any equation with respect to Pw, always remember this is the vapor pressure. Pw represent here vapor pressure at the surface temperature. I told earlier, in types of drying calculation we always taken consideration into wet bulb temperature. Here dry bulb temperature is not used for calculation for any drying calculation. A is the area, A means area, kg means overall mass transfer coefficient. If we are using this formula, from this also we can get the moisture removal rate. So then again, if we applying enthalpy value and heat transfer coefficient value, then you can use this formula for calculation of moisture removal rate. Using heat transfer coefficient, then we can go for this equation, and when we are given the mass transfer coefficient value, then we are using this formula to calculate the moisture removal time. Here HW minus HA is equal to humidity ratio, difference between these two. Difference means heated air temperature at product surface temperature, that will represent as humidity. Means when you are calculating the mass transfer coefficient, we put this value, humidity value, and in terms of heat transfer coefficient we put this temperature value. So constant drying period, as I told earlier, means if we are want to know this time value, so means whatever the moisture is removed by divided by the rate of drying. Means if we are assume kg water is equal to unit of this much amount of water is removed, area is equal to meter square, and rate is equal to simple and this time value will become, here md is equal to what are the weight of this dry solid after this completing this entire process. Then for if we want to calculate the falling rate period, drying time period, then we can go for this equation. So X is the critical moisture content, X is the equilibrium moisture content, A is the area, RC is the rate constant, and here ln value is given also. So if we are sorting this equation, this is also gives us the short value. So majority of time you go for this equation, and total drying time may be constant rate drying time plus falling rate drying time. If we sum two, then that will give us the total drying time. Means whatever the moisture is removed with respect to rate of this constant rate falling period, and then ln value of this moisture content. It is the critical moisture content value, and this is the initial moisture content value, this is the final moisture content value. This is the rate of this falling period, and this is the rate value of this constant rate period. When we are going for any types of drying calculation, so majority of time we go for different types of mathematical equation. So it is not in your syllabus or not enlisted in a book. For your reference or for any types of comparative exam, 2 to 3 formula is very important. Henderson model, you remember this formula, Henderson and Page model is very important. So most of the time these two formula or this first 3 formula are asked in GATE exam. So they are giving the moisture ratio value, they are giving the time value. So you need to calculate. Example, if you go for this Henderson model, means moisture ratio A exp minus KT. Here A is equal to constant, K is equal to constant, and T value, T is the time, and here is the MR is the moisture ratio. Maybe for example A value, K value and T value is given, and they told find out the moisture ratio value using Henderson model. Then you have to remember this formula, AMR is equal to A exp minus KT. So Weibull model and Fick's law. Fick's diffusion is mainly imported in mass transfer model. From this mass transfer concept, this Fick's law is came for drying calculation. Here as I told, ABCD is equal to coefficient, and K, whatever you see this K value, this K value is the rate constant, and N is equal to model constant. And if you are calculating this Fick's law, then you remember one thing, whatever the thickness you are given any question or any exam, you need to put this half thickness. For example, 5 centimeter thickness is provided in question paper. So when you are solving this problem, you need to put 2.5 in centimeter. Means this Fick's law, if you are putting this value, you need to put in centimeter and half thickness value. If they are directly mention half thickness value, then it is okay. If they are not mentioning the half thickness, or they simply written the thickness value of this material is this much, then you need to divide it by 2 and then write this value in terms of centimeter. Then only you got the right answer. So the next is the drying rate and moisture content. If you want to plot this like moisture content and drying time, it is the experimental data. They are presenting like this, means up to here you can say this, after some time this will go like this and this will go like this, means up to that it is the constant rate, and entire this process is the falling rate period. Means initial you assume 100 minute is constant rate period, and then from 100 to 1400 minute is the falling rate period. Means majority of time moisture will remove, entire this process will fall by falling rate period, and it will take for sure, for example here it will take this much amount. In case of constant rate period, it will take only 100 minutes from this graph. So here also you can see that if this black line is present in 40 degrees Celsius temperature value, and this blue line represented 60 degree value. So there is huge difference between this process. Here 60 degree temperature is end in somewhat in 700 minutes, but in 40 degrees Celsius that is end in 1400 minutes, means almost double. 20 degree temperature difference, but practically gives us double value in terms of getting the same moisture content of the food product. So another thing that is represent is the drying rate. Is the trends that material are follow during this removal of moisture or in terms of moisture content. So initially you can see that will go like that very rapidly. The drying rate is follow very rapidly, and then again some rise in that, and again that is going to slow on that. From that it is very rapidly going, and then this you can show this the first falling rate period, and this one you can told as the second falling rate period, and from this zone you can known as the constant rate. Means initially this zone rapidly moisture is removed, and then after some time it will glow like this way. This is represent, this blue line also represent 60 degree value, and this 40 degrees Celsius you can show this is represent in black line. So this drying rate also huge difference also represent here, you see from this graph also. Then the last thing is the what are the relationship between water activity and deterioration reaction of the food product. So in this direction they represented as a deterioration rate, or here you see that the water activity of this food product. From here it is 0 to 1, and this is the rate. Means if you are going this direction, this rate will be got increased, and if you are moving this direction, this water activity value also increase. Here is 3 and 3, means total 6 types of deterioration processes takes place. First one is the lipid oxidation. This oxidation process follow these types of nature, means at 0.3 water activity this rate will be lesser, and if we are increasing the water activity to 0.7, at 0.7 water activity, 0.7 to 0.8 water activity, the lipid oxidation is increased, or this is the linear growth. Higher deterioration is takes place from if we are increasing the water activity 0.3 to 0.7, the deterioration process is also very high in case of lipid oxidation, and then from 0.10 0.85 up to that lipid oxidation is takes place. After that the lipid oxidation process is not takes place for deterioration. And then next one is the non-enzymatic browning. Non-enzymatic browning, if water activity 0.2, if any material having water activity greater than 0.21, so the deterioration also takes place, maybe non-enzymatic browning, means Maillard reaction takes place in that process. For that the rate will be increasing like this way, exponential increment of this, and after that after 0.75 it is also again reduced up to 0.95 water activity. This process from 0.25 or 0.2 to 0.7, this non-enzymatic browning process is takes place for deterioration. And then next one is the enzyme activity. It starts near about 0.3 water activity, and it's near about end with 0.8, somewhat at 0.8. So remember this value. enzyme activity starts in approximately at 0.8 water activity of this food material and stop at 0.8 water activity of the food material. And you also known as the mold, yeast or bacteria activity or deterioration process takes place if the material 0.7 or water activity value 0.7. So bacterial activity is start only if the material having moist water activity value is greater than 0.8, then only bacterial activity will start, otherwise no bacterial activity is takes place in that entire process. So yeast activity is near about after 0.75 water activity. If it is more, then yeast activity will be start, and mold activity if the material having water activity greater than 0.7, then the mold activity is responsible for deterioration of food product. So here some of the acceptable water activity value for unpacked dry food, means how much amount of moisture content or water activity value should be present on unpackaged condition for at 20 degrees Celsius. One thing you see, for chocolate milk it will be, for example, 0.68 the maximum permissible water activity value at 20 degrees Celsius, and you see majority of water activity value is lesser than point, except this 0.8, and potato flakes is 0.11 is the maximum permissible water activity value, and orange powder also 0.1, dehydrated meat 0.72 maximum, or dehydrated vegetable, for example pea 0.25. For dehydrated fruits you assume like this value is near about 0.3 approximately, and like dried egg like 0.3. For fruits, for hard candy approximately 0.25 to 0.3. For dried product you assume this water activity value 0.3. For example dried skim milk also 0.3. Roasted coffee, for roasted coffee this value starts from the 0.1, and wheat noodles, and thus it is, and in case of dried food except this orange powder, this 0.6 to 0.7 is the acceptable water activity value of this entire food product. So what we have learned from this course, we know the equilibrium concept, how this equilibrium, thermal equilibrium, chemical equilibrium is comes and gives us this concept of this ideal solution theory, and what are the Raoult's law, what are the equation for water activity, and how we can calculate water activity for different types of using salt solution or sucrose solution, what is the moisture content, and how we can find types of moisture content is present in the food material. Basics about drying means what are this is the constant rate drying period, falling rate drying period, and what is the process takes place during the entire drying process, what are the changes takes place during the drying process, and what are the mathematical formula that we can use for calculation of drying time, and what is the uses, how to select this, what is Henderson model, and what is Fick's law model for calculating of drying time, and what then the some water activity value of dried or packaged food product at 20 degrees